All right. Good morning, everybody. Welcome back. So today, let's pick up where we left on Monday. So our goal for today is to study acid-base reactions. Okay. So I will show you a lot of examples with some different situations. And I think that will be enough for us to understand the concept, and then we can move on to other things on Friday. Okay. And just a quick reminder, we will not have in-class assignment on Friday. Okay, so therefore, we will have regular lecture. Okay, so let me share my screen with you. Okay, so let's do here a quick recap. I defined for you acids and bases. So remember that according to the Arrhenius definition, acid is any substance that produces Ag plus in water, okay? So for example, here we have HCl, then when we dissolve it in water, it will split the hydrogen and produce chloride ions as well. So one thing I forgot to tell you, when we represent HCl with the hydrogen bonded to the chlorine, that's also called the molecular form of HCl. And when we have H plus and Cl minus, that's called the ionic form. And the same thing for bases. There is also the Arrhenius definition of base, any substance that produces HO minus in water. Just pay attention when you have more than one hydroxyl group in the base. So we have to take that into account when we dissociate the base and produce the ions in water. Okay, and then we get to the acid-base reactions. Acid-base reactions are also called neutralization reactions. Every time we have an acid reacting with a base, the products are going to be a salt, sorry, here I'm thinking in Portuguese, salt and water. Okay, so acid and base will react forming salt and water. And there are three ways to represent an acid-base reaction. The first one is called molecular equation. Second one is overall ionic equation. And the third one is called net ionic equation. Okay, just to be clear here, these three ways, they represent the same thing, an acid-base reaction producing salt and water. I want to tackle first the molecular equation for acid-base reactions, okay? So we will start with that, and then we will move on to overall ionic equation, and then a net ionic equation. Okay, very good. So the best way here is to show several examples until we understand the concept. So the first example that I want to start with is the reaction between hydrochloric acid and sodium hydroxide. Okay, so now it's the point of the course that you have to understand really, really, really well nomenclature. Okay, so that will be the basis for us to move on. Okay, and that's the kind of question that I will ask you. I will give you the name and you have to come up with the formula. So first example here is the reaction between hydrochloric acid. So hydrochloric acid is HCl, and that will react with sodium hydroxide. Sodium hydroxide is a base, and A hydroxide means we have an OH group. Okay, so then the formula is NaOH. So let's react both compounds, HCl plus NaOH. So we have here an acid reacting with a base. The result of this reaction is salt and water. So acid-base reactions are basically a double displacement reaction. So what's going to happen here is the hydrogen will combine with the OH part of the base, and that's going to produce HOH, which is water, and the sodium is going to combine with the chlorine, producing NaCl, which is a salt. Remember, always positive first and negative second. Okay, NaCl. Okay, acid plus base products are going to be salt and water. Always check to make sure the reaction is balanced out. And one important thing here, make sure that the charges of the cation and anion are correct. Okay, so let me show you. We will come back to this later. Let's do one more example here. So we are tackling here first the molecular equation. So now it's the reaction between hydrofluoric acid and calcium hydroxide. Hydrofluoric acid HF reacting with calcium hydroxide. Calcium is Ca. Because this is a hydroxide, it has to be an OH group following the calcium. And attention here, calcium belongs to the group 2. Therefore, it will acquire a 2+ charge to be stable. Hydroxyl groups are always 1-. Therefore, we need two hydroxyl groups for each calcium. Okay, so pay a lot of attention to the charges. Just a second. We have here calcium hydroxide. Again, acid reacting with a base, the result will be salt and water. And understand that this is a double displacement reaction. Hydrogen will always combine with the OH group, producing water. And in exchange, calcium is going to combine with fluorine to produce a salt. And in this case is calcium and fluoride. Now attention here to make sure you have the correct formula for the salt. You already did that before. I'm not changing anything here. The charge of calcium is 2 plus, and the charge of fluorine is 1 minus, because fluorine is in the group 17. Therefore, in this case, we must cross the charges, and that will result in an index 2 for the fluorine. Now, we need to check if the reaction is balanced or not. So you can see here that we have 2 fluorines in the product side and just 1 in the reagent side. So it's always a good idea to start with that, which means we need 2HF. Calcium, we have 1 here in the product side and 1 in the reagent side. That doesn't need to be balanced. And now let's check the hydrogens. We have 2 hydrogens for the 2HFs, and attention here, 2 for the base, a total of 4 hydrogens, which means we need to have 2 water molecules in the product site. With that, the reaction now is balanced. Okay, and just understand that we are performing all these reactions in water. Okay, so it's always aqueous media here for us to make things simple. Okay, and one important thing here that I almost forgot. Of course, you need to remember how to name the salt. And for salts, the first word is the name of the first element, calcium. And then we are going to write the name of the anion. In this case is fluorine. And when it's an anion, fluoride. Okay, remember about the IDE ending when you have F minus. Okay, so The first case I showed you, HCl plus NaOH, very simple reaction, 1 to 1 to 1. Now we have a slightly more complicated case because we have two hydroxyl groups. And with that, we are ready to tackle a third example here regarding the reaction between phosphoric acid and barium hydroxide. Okay, so phosphoric acid is an oxo acid. Remember about Nick the camel? So you are going to end up with PO4 as the phosphate. PO4 has a 3 minus charge that will be balanced out by 3 atoms of hydrogen. Okay, so therefore, phosphoric acid is H3PO4. And that will react with barium hydroxide, BaOH. Barium is in the group number 2, therefore the charge is 2 plus. Hydroxyl is always 1 minus, which results in BaOH2 for the base. Okay, so now let's write the reaction between phosphoric acid and barium hydroxide. So I'm going to write here in the corner. So we have H3PO4 plus BaOH2. Recognize that this is an acid-base reaction. The only two products formed in this kind of reaction, are salt and water. There is no other products formed. And now attention here, because this is a little more complex. Hydrogen will always combine with OH, forming water. And in exchange, barium is going to combine with phosphate. And that will produce a salt, BaPO4. Now that you know the kind of the formula of the salt, the next step is to make sure about the charges, and if needed, cross the charges. Barium is 2 plus. Phosphate is 3 minus. Very, very careful with that. Okay, so remember about Nick the camel. So phosphate is Phoenix, PO4, 3 minus. Cross the charges. So very careful here because you have to pay attention when you cross the charges when you have an oxo anion. So the 3 will come down here to the barium, and the 2, attention, now will multiply all the group phosphate. Okay, so you have to indicate that in between parentheses. So that here means that in this structure, we have 3 barium ions and 2 phosphate ions, okay? So that's why we need to make sure the phosphate is in between parentheses, okay? That will indicate that we have two phosphate groups in the structure. And of course, the name of the salt, barium. And then when we have an oxo anion, that is phosphate, okay? ATE at the end. Therefore, Ba3PO42, barium phosphate. Okay, so very good. So now the next step to finish up the reaction is to make sure the reaction is balanced out. So I always like to start with the negative part of the salt. That's just personal preference. You do whatever you want to do. So for the reagent side, we have two phosphate groups. What we are going to do is to add 2 as the stoichiometric coefficient in front of the acid. The second step that I like to do in when balancing this kind of reactions, now it's to look at the positive part of the salt. You can see here that we have 3 barium ions. Therefore, we are going to add a 3 in front of the base as our stoichiometric coefficient. And here is going to be a number 1. And what is left to be balanced out is the water molecule. So let me give a little more space here. Okay, so let's see how many hydrogens we have. 2 times 3, that's 6 hydrogens for the acid. Attention here, 3 times 2, that's 6 hydrogens in the base, which means we have 12 hydrogens in the reagent side. The only place to balance out the hydrogens is the water, which means we need 6 water molecules. 6 times 2, that is 12 hydrogens. So we are all good. If you wanna double check the number of oxygens just to make sure you balanced out correctly, you can do that. It has to match, okay? So we have 6 hydrogens from the water, and attention here, 2 times 4, which is 8 from the phosphate, total of 14, and that's going to be 8 plus 6, a total of 14 in the reagent side as well. So that's how you write molecular equations when you have acids reacting with bases. Remember, the only 2 products possible in this kind of reactions are salt and water. Pay attention to the charges. make sure you have the correct formula of the reagents, make sure you cross the charges when you form the salt, and then the final step would be to balance out the reaction. Okay, and as I told you before, all these reactions are performed in water. So the next thing here that we have to tackle is what happens when we have a salt in water. Every time you have a salt in water, there are two different things that may happen to this salt. So let's give here, for example, let's start with NaCl, sodium chloride. So the formula of this compound means that we have a sodium plus bonded to a Cl minus, okay? So positive and negative, they have a very strong interaction that will keep the solid together. When we dissolve or when we add the salt in water, the water may be strong enough to split the salt and separate sodium and chloride, okay? So that's the first possibility. Or the water will not be strong enough to separate the sodium and chlorides, and they will stay together. Okay, so again, salt is composed, in this case, of sodium plus interacting with Cl minus. So in the solid state, they have a very strong interaction. However, when we add water to the salt, two things can happen. The water is strong enough to split the ions, or the water is not strong enough to split the ions. If the first option happens and the water is strong enough to split the ions, then we call the salt soluble. The other way around, if NaCl is not split and it keeps its identity in water, we will call this salt insoluble. How do I know when a salt is soluble or insoluble? Two ways to figure that out. You go to the lab and you perform the experiment, or you will check solubility tables. Okay, because we don't have a lot of experience in the lab, we are going to use the solubility tables. And I'm showing you here what this table looks like. So let's look at the first row of the table. If we have ions from the group 1, the first group of the periodic table, that will yield salts that are always soluble in water. And there are no exceptions for salts from group 1. Okay, so that's what this table means. Okay, first column is the ion that is part of the salt. The second column tells you if it is soluble or not. And the third column will give you some sort of exceptions if there is any. So we will always check the solubility table to make sure that the salt is dissolved in water or it is not dissolved in water. It's a solid. Okay, so for example, here, looking at the fourth row of the solubility table, every time you have a salt formed by chloride, bromide, or iodide, that will yield soluble salts. But there is one exception, and the exception states that if you have silver plus, lead 2 plus, or mercury 2 plus in the structure of the salt, then that will result in a not soluble salt. Okay, very good. So now it's a very good time for us to go back and tackle overall ionic equation and net ionic equations. And to write this kind of equations, we are going to need to use the solubility tables all the time. Okay, so there is no point to memorize this table. We can always go back and check it, and that's what we will do. Okay, so you need to understand the concept, not to memorize things. Okay, so let's go back all the way to the first example, hydrochloric acid reacting with sodium hydroxide. We know that it will produce salts and water, and we know that the salt is sodium chloride. Remember, always when you write the molecular equation, you are going to use HCl and NaOH. What is the difference when you write overall ionic equation or net ionic equation? In those cases, now you are going to represent the ions that are involved in the reaction. Okay, so to write ionic equations, the first thing that I like to do is to write the formula of the acid. If we are dealing with ions, the first thing we have to do is to dissolve this acid in water. Every time you dissolve an acid in water, you are going to split the bond, in this case, between hydrogen and chloride. And by definition, you will produce H plus and Cl minus. Now, very important thing here, and you will need to do that. Now, because these ions are dissolved in water, we must put in parentheses AQ. Okay, remember that AQ means aqueous. In other words, ions dissolved in water. And we do the same thing for the base. NaOH. Let's do here a pre-reaction and dissolve this compound in water. In this case, we are going to break the bond between sodium and hydroxyl, producing Na plus. Remember that this is 1 plus because sodium belongs to the group 1, and OH minus. And the same thing here. Now the ions are dissolved in water. Therefore, we need to represent, we need to add AQ in between parentheses to represent that. Okay, so now what I have is all the reagents in the ionic form. And then you do the same thing basically that you did before. So see now here why the hydrogen is going to go with the OH, because we have H plus, OH minus. So positive attracts negative, and that will always form water. Now we need to represent the physical state, which is a liquid. And sodium, because it's positive, will attract Cl minus because it is negative. And we know from the molecular equation that this will form sodium chloride. Now, attention here, very important thing. We are represent everything as ions. Sodium chloride in water is the identity of this compound. Sodium strongly bonded to chlorine forming a solid, or are they sodium plus and Cl minus? So to make sure you get this right, if it is sodium plus Cl minus, that means the salt is soluble. If you need to represent as NaCl as 1 unit, that means the salt is not soluble. How do I know when the salt is soluble or not? Well, we go all the way down to the solubility table. Sodium belongs to the group 1, therefore always forms soluble salts, and there are no exceptions. Therefore, because NaCl is soluble, we must represent that as NaAQ plus Cl minus AQ. Plus water, of course, because that is the other product. And here, that's the major difference between molecular equation and any kind of ionic equation, okay? And in this case, we have the overall ionic equation. So the only different thing here that I did was to represent the acid in the ionic form and the base in the ionic form. That will result always in water and the salt. To decide if the salt is Na plus and Cl minus, or just NaCl as 1 unit, you check the solubility tables. In this case, is soluble, therefore we have sodium plus and Cl minus. And that's how you write your overall ionic equation. And then just make sure everything is balanced out. Okay, so if you wrote the overall ionic equation, now the net ionic equation is super easy. So we are going to treat the overall ionic equation as a mathematical equation to write the net ionic equation. So that means if a compound shows up in the reagent and in the product side, we can cancel out. Okay? It has to be exactly the same thing. So let's take a look. Sodium plus shows up in the reagent side and is exactly the same thing as Na plus in the reagent side. So for the net ionic equation, we are not going to show sodium plus. So that will be canceled. The same thing with Cl minus and Cl minus. H plus, there is H plus in the reagent side, but there is no H plus in the product side. It has to be exactly the same thing. So we cannot cancel. And OH minus also in the reagent side, but not in the product side. And water only in the product side, nothing in the reagent side. Therefore, the net ionic equation, H plus reacting with OH minus, resulting in water. Okay, so see the progression between molecular equation, overall ionic equation, and net ionic equation. Okay, so we have time to tackle here the second example. So I would like to do that before we finish up for today. Okay, so HF reacting with CaOH2. So let's do, now that we know the molecular equation, let's write the overall ionic equation for this reaction and then the net ionic equation as well. So here is the trick. When you have stoichiometric coefficients that are not 1, so we are going to carry over what we already balanced out for HF. So in this case, I know that we must have 2 HFs because this number came from here, okay? So let's dissolve the 2 HFs in water, so that will split up the bond between hydrogen and fluoride, producing H plus AQ and F minus AQ. We started with 2, therefore we have to end up with 2. And we are going to do the same thing for the base, calcium hydroxide. Okay, so let's dissolve calcium hydroxide in water. So that will break the interaction between calcium 2 plus, attention here, calcium 2 plus, because it belongs to the group 2, AQ. And very careful here, this index 2 in the formula means that we are going to produce 2 hydroxyl ions in water, okay? So the index 2, when you dissolve the base in water, becomes the stoichiometric coefficient. Now the reagents are in the ionic form. So we need to produce salt and water. H plus is going to combine with OH minus. And we know that this will produce 2 water molecules. And in exchange, calcium is going to attract fluoride, forming a salt. We know the identity of the salt from the molecular equation. We know that this is CaF2. Now, because we have ionic equation, we have to decide, is CaF2 in water Ca2 plus and F minus, or is it 1 unit CaF2? Let's look at the solubility table. We have here a salt formed by fluoride. So look at the last row in this table. Fluorides are always, they are usually insoluble. The exception is group 1 or ammonium. Calcium does not belong to the group 1, which means calcium fluoride, it's not soluble in water. If it is not soluble in water, we are going to represent this salt as an unit CaF2, and this is a solid. Okay, an alternative way that you may represent that you have a solid being formed is to write an arrow down. Okay, so that means something is precipitating. So, which means that when you mix HF and CaOH2 in water, you form a solid, and the identity of the solid is CaF2. Okay, so we have a question here. How does one know which part of the salt to reference regarding the solubility chart? Okay, so very good question. It doesn't matter, okay? So you can use the positive part or the negative part. So whatever you find in the table, that should be enough. For CaF2, the only thing that relates to the table is the negative part, and that's what you are going to use. Okay, so just give me an extra minute here because I want to write the net ionic equation and then we can finish up. Okay, so for the net ionic equation, you are going to cancel out everything that shows up in one side and in the other side. It has to be identically the same thing. H plus, you don't have in both sides, therefore it will show up in the net ionic equation. Fluoride, same thing. You don't have fluoride in both sides of the equation, it has to be exactly the same thing, okay? So therefore, it will show up in the net ionic equation. Calcium 2 plus by itself does not show up in both sides of the equation. Therefore, we cannot cancel. And OH minus also does not show up in both sides of the equation, cannot be canceled out. In the product side, CaF2 solid does not show up in both sides as well, cannot be canceled, and water in the liquid state also does not show up in both sides. So when you have the formation of a solid, the overall ionic equation is going to be identical to the net ionic equation. Okay. And that's how you write molecular equation, overall ionic equation, and net ionic equation. So that will be enough for today. And on Friday, we will finish the last example and then move on with new things. Okay, so that will be enough for today. And I will finish at this point.